All right, we have the last talk for today. Please welcome, Brian, who's going to talk to us about how he built the Backblaze Vault that actually stores all of the backup data that Backblaze takes in.
All right.
Welcome, Brian.
Thank you. Hi, everybody. Thanks for sticking around all day for the last talk. I appreciate your diligence and endurance. Today I'm going to talk about Backblaze and our new storage architecture. I'll try not to repeat too much of what has been said before because a lot of it's going to be the same kind of architecture. But there are two key decisions we made I want to hit on that weren't obvious from the outset that I think are interesting. First of all, though, what is Backblaze? A couple of people have come up to me and said hi today and looked at my name tag and said, Backblaze, what is that? We do online backup. So you can install an app on your Windows or Mac computer, and it sends all the files up to the cloud, which we happen to build. And that's about it. It's a cheap service. We think it's really good. And we currently have 150 petabytes of storage in our data center. The company is now 7 years old. I've been with Backblaze for a year and a half. The thing that really drew me to the company was the fact that it was bootstrapped from the ground up and really funded by the revenue from the company. The founders didn't take any venture capital to get the company going. So the company started out with 5 founders who all committed to work for a year without salary. They each put in a little bit of money, and from there they built the company up on the $5 a month that each subscriber pays. It actually took 15, 18 months before they started taking minimum wage. But it's ramped up from there, and now it's a 35-person company paying real salaries and backing up 150 petabytes of data. I want to put in a shameless plug here for Backup Awareness Month, which is June. It was started by one of our esteemed competitors. We do a survey annually on how many people back up their computers and how often. 17% of computer owners back up their computer once a week or more often. That's not nearly enough. That's the reason people need a product like this. Because, as everybody said, hard drives die, computers die, you need to have your data backed up. So when the company started out, the original thought was to write an app, rent some storage on S3 or somewhere, and make lots of money. It turned out that didn't work so well because S3 was too expensive. Looking at the average customer at that time, $5 a month, it just didn't work out. Any profit margin, actually it came out to be a loss margin, which wasn't a good investment. So they designed the Backblaze Storage Pod, which is a 4U rack mount enclosure. It holds 45 drives. So I think it's clear which side of the 4 drives versus 90 drives we're on. Clearly more on the 90 drive side. Partly because we don't do that much computing. It's just storage. So if we had extra processors sitting around, it really wouldn't do us a lot of good. There's been some news the past few days about Facebook and the Open Compute project and how Facebook invented open source hardware. I'd like to contest that. Backblaze open sourced the hardware design for the storage pod 6 years ago. That was version 1.0. We're now on version 4.5. And it's still going strong. There are other companies out there building the same design. You can buy this product. Ours is red, theirs is yellow, but it's basically the same thing. So I think I'll take a sidestep here and talk a little bit about the architecture of the backup products to give some context for what I'm going to say later. I don't have a slide about this, but it's a really low overhead architecture where the storage pod runs software to receive files. The app on your computer sends the files up, and it talks directly to the storage pod. There are a couple other components in the system, but they're fairly small and simple. One is the load balancer, whose job is not to route traffic through it, but to tell the clients who to talk to. So if your computer wants to back up files, it talks to the load balancer and says, give me a URL to send files to. And the load balancer gives it a URL for one of the storage pods. Each of the storage pods has its own public IP address, and the files just get uploaded to it. So that makes the infrastructure is pretty simple. We just need a network connection between the storage pods and the computers out there in the field. But it means that storage pods need to do a little management on their own of load balancing. If they start getting too busy, they'll kick a client off, who will then go back to the load balancer and say, okay, who should I talk to? That one didn't work. And the whole system just evens out really well. The other advantage of that is that it handles peak traffic really well. Typically, we'll be deploying new storage pods every week as time goes on, and the new ones are empty, so they take the bulk of the traffic. But there's a little bit of room in all the other storage pods throughout the data center. We've got over 1,000 of them now. So there can be a huge peak in traffic, and all the pods can be taking data during that peak, and it doesn't cause any problems at all. Now, what's inside the storage pod, traditionally, up until recently, was standard Linux RAID. There were 45 drives in there, divided into 3 RAIDs, 15 drives each. And then on top of the RAID, we run ext4. And on top of that, the files get dropped. One more quick aside here. The files sent up from the clients are all encrypted because we consider your files to be private. So we never have the data in the clear on the service. Not only that, the file names are private. So the third part of our service is the metadata storage that lists all the file names and their mapping to the files on the various storage pods. Those files are also encrypted and secret. So the backup client periodically uploads its current index of files, but before doing that, encrypts it. So when you need to restore your files, you need to provide the password for them to be decrypted. So the RAID works pretty well. There's plenty of availability for backing up, because if a couple pods go down for maintenance or whatever, there are plenty of other pods to back up to. But if you want to file back, you may have to wait for that pod to come up, because it's just in that one computer. For the original backup product, that worked fine. We promised 24-hour turnaround. You order a replacement drive, we'll dump your data on it, mail it out. We could afford to wait a couple hours for the pod to come back up. But now that we have iOS and Android apps to browse through your files, that doesn't work so well. You don't want to wait a couple hours to look at that photo that you just lost, or browse through that PowerPoint presentation that you just lost. So we need more availability. And the answer, I'm sure you guessed this, is to distribute the files across multiple computers, so multiple storage pods. We put them in groups of 20, one in each rack. So one rack going down won't take down a vault. And the overall architecture of this 20 storage pods is called a vault. And then one drive from each of those storage pods we call a tome. So that's basically a target for a file. When you upload a file, the backup client still talks directly to the storage pods. So sends the file to a storage pod. This pod then shards the file, stripes it across the shards, computes the parity, and then distributes those shards to its siblings within the vault. I think that's about all there is to say about that. That part's pretty straightforward. We wrote all the code for the striping and the parity computation and distributing these shards across the different pods in the vault. That's actually pretty straightforward. A little trickier was the load management. Because the clients are backing up directly to the storage pods, we need to be able to tell them to go talk to somebody else when these pods get too busy. So the vault is designed to very smoothly degrade as the load rises. When that happens, it tells the load balancer, and load balancer sends people to other pods. When it gets too extreme, it'll start kicking clients off, and then they'll go somewhere else on their own. But that doesn't happen very often. So again, the key here is gradual, nice degradation as the load in the vault increases. So we started this project just about a year ago. I think it was May of last year, with a few goals. Mainly, we needed to replicate the functionality of our existing storage pods with more availability. We need to be able to access the files anytime, upload anytime. And our design targets were to be able to ingest incoming data at 2.5 gigabytes per second, which matches what the old pods could do. Each individual pod before could accept 1 gigabit of data per second. Multiply that by 20, you get 2.5 gigabytes per second. And that's the raw files coming in. In the backup product, the average file size that's sent up is about 10 megabytes. It breaks up big files into small pieces and groups small files into big pieces, so it comes out about 10 megabytes. For vaults, though, we wanted to do better. We wanted to do an average file size of 1 megabyte to allow other applications with smaller file sizes. But we still wanted the same speed. And then the other big constraint was that we didn't have very many engineers. After I started a year and a half ago, that brought the engineering team up to a total of 5 people. And we couldn't have all of them working on it because there were still other things to do. So we allocated 2.5 of us to work on vaults. And I don't know what the magic number about 9 months is. It actually took us about 8.5 months between project inception and launching it in production. And since then, we've tuned up a few things, but it's been working solidly and reliably since then. There were a couple changes we needed to make to the storage pods themselves for this architecture to work. The two big ones were memory and networking. The older storage pods had 8 gigabytes each. That wasn't enough. It's enough to run the JVM. All our stuff is in Java. We currently have an 8 gigabyte JVM, and then there's Linux and a couple of little things. But the bulk of that is actually for file system cache. Because we run directly on top of ext4, we need a lot of directories to be cached so we can quickly get at the files. So that other 24 gigabytes is mostly file system cache. And then the older storage pods had a 1 gigabit networking interface. If we need each pod accepting a gigabyte of data, sharding it, and sending it out, that's a second gigabit it needs to be talking. And then it's also accepting shards from the other pods. So that's a third gigabit. So we basically needed 3 gigabits on each pod. They don't sell 3 gigabit networking, so we went with 10. And then the last one, Tim really wanted to do, but I don't think it was necessary. We boosted the speed on the SATA. I don't think that's by any means the bottleneck. Our main bottleneck is just number of disk IOs per second, given the file sizes we're doing. So I said before I was going to talk about 2 design decisions that weren't obvious from the outset. One is we do resolve encoding, and we do it in Java. Most production systems don't do that. You can get encoding a lot faster if you go with the vector instructions on Intel processors and you write it in C and assembly. But it turns out we didn't need that. Right now, we're pretty well balanced between processor and disk I/O. When a new vault is deployed, it's empty. It's sucking in data at over 2 gigabytes per second. The CPUs run 70 to 80%. The disks run 70 to 80%, and we're pretty happy with that. So we didn't need anything faster, and it was really easy just to write up some Java code and get it running. Did a fair amount of performance tuning because I still didn't believe it was going to be fast enough in Java. We coded up the same algorithms in C and tried different things, tried different buffer alignments, and the just-in-time compiler in Java is just really good these days. I was amazed. It's the same speed as the C. So it's actually doing a bunch of stuff. It's inlining methods on its own. It's rearranging instructions. And it's making the code run really fast. So I had a hand-coded C implementation explicitly telling what methods to inline. For the inner loop, compared to the Java, they're the same speed. What actually matters more, if you're not doing the vector instructions, which will buy you a lot if you need that, what matters more is the buffer alignment. The processors we use have a 8-way associative first-level cache. So if you've got 20 shards, they won't, and they all happen to line up on the same cache line, which is the obvious way to allocate them, the performance drops by a factor of 2 or 3. If you carefully hand-tune the alignment, it gets really good. But then you've optimized it for that particular processor and that particular memory configuration, and it might detune in other cases. What we found was doing a very stupid thing in Java, which is allocating each of the 20 buffers just as a byte array on the heap. Kind of randomizes their placement in the cache, and it's only about a 20% loss over hand-tuned buffer alignments. So we went with that. It's easy. It's not perfect, but it's good enough for us. Oh, And final news, as of yesterday, we open sourced our Reed Solomon code. It's on GitHub, so go take a look and enjoy it. And the other decision I didn't think we'd be able to do was just running all of this on top of ext4. So basically, each storage pod in the vault, each drive has its own ext4 file system that just stores the shards. Each shard is one file in a file system. They're not that big, which means there's a fair amount of overhead in terms of number of IOs. To write a given amount of data, you've got to write lots of little files. But ext4 is actually pretty good when you're just dumping the file in on an empty disk. It'll line them up nicely as long as you tell it ahead of time how big each file is, so it knows how much space to allocate. It goes pretty fast. And even on the reading side, there are a couple of optimizations we did, but the reading also goes fast enough for us. The process of rebuilding a drive, you go through and you scan all the files in its sibling pods and you dump data onto it. That scan, if you do it in the same order that you wrote them, goes pretty fast. And as I mentioned before, it does take a fair amount of money to cache the directories because we couldn't hand tune that ourselves and tell it which things we need cached and which things we didn't. So I'm sure it's caching things we don't need cached in addition to the things we do need cached. And then there's a bunch of housekeeping code in the background going through and doing a variety of things, as Kęstutis mentioned on the Facebook system. It's going through reading every shard and every drive periodically just to make sure that it's not corrupted. Each one's protected with a good strong checksum. So if bits fall off the disk, we'll know about it, or if the disk just fails to read that particular sector. It's going through and it's comparing between siblings in a tome. It'll scan through all the drives and make sure they have the same set of files. And then this is a quick view of our ops team's view of Into the Vault, saying how things are going. This is one vault showing the first 9 tomes. If you care what those numbers are, the third column of numbers is the total amount of space on the tome. These are 4 terabyte drives. So that's approximately 17, which is the number of data shards, times 4 terabytes minus some overhead. The second column numbers is the free space. And the fourth column of numbers is the number of clients uploading files to that pod right now. And then the rightmost is the scanning between and synchronization, just saying they're all healthy. Now there's a question on Kęstutis' talk about how do we know drives go bad. I can talk about that a little bit. Back on Linux RAID, it was really bad when a drive went bad because the RAID system isn't really smart about things like that, surprisingly. If it recognizes the drive goes bad and it wants to rebuild, it'll start scanning through all the drives. And it says, oh, there's a bad sector on this drive, I'll drop it out. And it doesn't read any more data from that drive. And it's marching through and it says, oh, there's a bad sector on this drive, I'll drop that one out and keep going. Meanwhile, all the other sectors were fine. The data was perfectly readable, but the RAID gave up on it. So we wound up having to sometimes hand copy the drives and then put them back in the RAID and then let it rebuild. And that was just annoying. So we were pretty conservative about deciding when a drive was bad. We look at the smart stats every day, and the biggest one was pending sectors. So sectors that have gone bad and reallocated sectors. Sectors that have gone bad and then been moved somewhere else. As that number started going up, we would just toss the drive out and stick a new one in before anything could go wrong. Now that we have the Vault architecture, we're less sensitive to individual files falling onto the drive because we can just fix that one and then read the rest. So we're going with more of a wait and see. Wait until the drive really does fail or really does get too slow, and then we'll take it out. So if it becomes totally unresponsive, it's out of here. Or if it's too slow, and that we're measuring by looking across the tome. So the 20 drives that are together storing files, we compare their performance because they have pretty much the same load. They're all reading and writing the same set of files. If one of them gets markedly slower than the others, we take that as a sign that that drive is going bad and something needs to happen about it. And marketing is listed on this slide. The numbers on the last point are just made-up numbers based on how we number the vaults and the pods within the vault. But the key point is horizontal scaling. Our system doesn't really have a central point that manages the data. So if we need more storage, we stamp out more vaults. And finally, we're counting this project as a success. This slide was made last week, so it's out of date. We have 5 vaults in production now as of yesterday with about 18 petabytes of storage. Everything is going smoothly. Files are getting backed up, files are getting restored, and we're very happy with it. Any questions? Let's see, microphone's coming.
So I probably missed something, but I just wanted to ask you that if the
Sorry?
drives fail, right, when the drives fail, then you need to rebalance so that you get back the same parity,
Exactly.
same protection level. So is there a mechanism that you do that automatically, or does it require manual intervention?
So it does that all automatically. It's continually scanning each tome, comparing all 20 drives to make sure they have the same set of shards. If one of them doesn't, which happens if you drop in a new drive, then it starts rebuilding. There are basically 2 paths for that. One path is random shards missing here and there, or something just doesn't look right. It'll do a full comparison of all of them, and there's some complex logic to figure out who's right and fix it. In the case where one shard is just missing out of the 20, after you replace the drive, there's a fast code path there. So it'll just zoom through that drive, recomputing the shards, and it uses all 20 pods. So all 20 CPUs in the vault stream files off all drives, recompute, and then dump them back on that one drive. So Kostis was saying their target was under a week. Our target was actually 2 days, and we're just about there to rebuild the drive. Back here.
I probably missed something, but at the beginning of the slide, I believe you said that you had 150 petabytes. I believe you said you had 150 petabytes backed up, yes?
We have 150 petabytes, that's right.
And then you said you had 5 volts at 14 petabytes. Where are the other 70?
They're on the old storage pods. We're
Oh,
in
cool.
RAID.
All right.
We're in the process of migrating. We have a nice automatic migration system. We're not in a giant hurry because the old ones work, except for some disk drive models that are bad. Getting those off those really fast. Yeah, so it's just going to be a gradual migration process. Because the hardware for the vault pods is slightly different, we have a cost trade-off. Is it worth it migrating off the old pods if we can't use them for vaults directly? We'd have to upgrade the hardware. Do we want to put the money into that? So it's going to be a slow process of migrating off of them.
How do you manage your software upgrades in your data center?
Software upgrades are always awesome. Because each vault operates pretty much independently, we don't have many APIs in between components of the system that we need to worry about. So it's kind of like that talk earlier about the Outlook system. Each vault has all of its pieces, and we just upgrade the whole thing at once, and it comes back up. There are a few APIs facing outside the vault that we need to preserve, especially the ones that talk to the clients in the field, because they might be 2 years old. You have to keep those APIs maintained. Beyond that, it's a fairly straightforward process. In terms of keeping the vault up and running, which may be what you're asking about, we just do one pod at a time and go through it.
So at Facebook, we love what your company does and publishes on the web. So I cannot show, but whenever you publish your blog post about drive reliability, everyone is sending links around and saying, just have you read what Backblaze guys posted? So we love that, and we're bound by many of these rules with our vendors where we cannot share this data, and you're sharing. So it's very interesting. I have 2 questions.
Okay.
What's your using smart to predict and detect a disk failure? It's quite controversial. What's your take on this one? Second question.
Sorry, I didn't quite get that.
First question, using smart counters to predict and detect failure of a hard drive. What's your take on this? There is a controversy in the industry. Some people say it's very valuable. Some people say it's useless. Second question, predicting a failure of a drive and using machine learning and all these sophisticated techniques. Where do you stand on this?
Okay, so predicting drive failure based on smart. I've done several blog posts about that, and I'll put another shameless plug. We actually publish all of our data. If you want to have a go at it, go for it and let us know what you find out. So we capture smart stats for all of our 40-some thousand disk drives every day. All that data is available to you if you want to look at it. I've done some analysis, looked at every smart stat versus drive failure and see if there's any correlation. Not fancy machine learning stuff, but just raw correlations. Some of them were circular reasoning because we use pending sectors to count a drive as failed. We can't really see if failed drives have bad pending sectors because obviously they do. Those are the ones we pull out. Now with the vaults, we'll be able to test that. Some of the other ones, there were some clear correlations that we didn't quite understand. The drive manufacturers won't tell us what they mean, so that's kind of frustrating. We actually talked to a company, I don't think I can say its name, that does machine learning and took all our data. They didn't come up with much. So in terms of predicting drive failures from smart, I'm not that optimistic. That's why we're going with just wait until they die, now that we have the vaults and we can afford to let them die. All right?
Since you back up so much data, have you looked at deduping? You didn't talk about it at all.
Sorry,
deduping?
Hard to hear over the fan.
Deduping? I mean, finding duplicate blocks and just eliminating them so that your storage costs actually go down? I mean,
No,
in your stack, you never talked about it. And that is majorly, I mean, Aaron was talking about all this tape versus disk. One of the things you can do with the tape is deduping. And I was just wondering why you guys have never explored that.
Okay, so I think the first question was about deduping files, and what if two people upload the same file?
Yeah. Or the blocks.
We don't know that. All the files are encrypted with different keys, so we can't even compare the encrypted files to see if they're the same file. The app that runs on your computer will dedupe, so if you have two copies of the same file, it'll take care of that and won't upload both to the data center. But if everybody here has the same kitten video on their hard drive, we'll just have that many copies of it because we don't know which file contains what. Sorry, what was the second question again?
Yeah.
Just real quick.
Yeah, that's the question.
Okay.
Do you do file level backup or disk level backup? So for example, if I have huge files and incremental backup, will it work with your system?
Okay, we do file-based backup. So that works well for a lot of things. VMware images, not so good. Some other files that are huge files with a few places that change, it doesn't work that well. Obviously, we could do some optimization there, but it hasn't been that big a deal.
Okay. Thank you.